Hello everyone, my name is Homer Papadopoulos. I'm a 10th grade student in the Hellenic College of Thessaloniki, and my presentation is going to be about Thomas Young's double-slit experiment, how to recreate it at home, and why it is important. Additionally, I would also like to thank Banani Gem for editing this presentation, and I hope that you will enjoy it. So, in today's world, we scientists and students all want to improve quantum physics by searching for new information. However, we must not forget how we managed to get to this point and how it all started. So we're going to talk about the world's first ever quantum physics experiment and how it helped with the help of the scientists of the past shape our perception of the universe and physics forever. So, we need to start from something pretty simple. A single word. Light. So, you might be asking, what is light? Well, one could say that light is the spectrum of electromagnetic radiation that is visible to us, ranging from 400 to 700 nanometers. That's at least the textbook definition. And you are probably going to say that we already know that. So, let's ask a different question. How does light work? Well, the nature of light has been a subject of debate for centuries. The first one to work with light was Descartes, who assumed, although incorrectly, that light travels faster in denser mediums based on the way that sound waves work, thus reaching the conclusion that light functions as a wave. However, light has to travel through a medium, right? But what happens in space, where there is no medium since it's a vacuum? Well, for that, there were two theories that were the most prominent. The first one was the wave theory. Huygens had suggested that light waves travel through space, mediated by the ether, an invisible and weightless substance that exists throughout air and space. The search for ether was quite notable during the 19th century and before being disproven. It lasted until the late 1800s based on the evidence by Charles Wheatstone's proposed model demonstrating that ether carried light waves by vibrating at an angle perpendicular to the direction of light propagation, and James Clerk Maxwell's detailed models describing the construction of this invisible substance. The second theory was the particle theory, also known as the corpuscular theory of light, which states that light is made of small particles called corpuscles, which means little particles, that travel in a straight line with finite velocity and possess momentum. Isaac Newton laid the foundation for this theory through his work in optics. This early conception of the particle theory of light was a predecessor to the modern understanding of photons. This theory came to dominate conceptions of light in the 18th century, displacing the previously prominent vibration theories, where light was viewed as pressure of the medium rather than between the source and the receiver, which was first described by Descartes and later refined by Huygens, while in part was correct and managing to explain successfully refraction, reflection, rectilinear propagation, and diffraction, it would fall out in the early 19th century as the wave theory of light amassed experimental evidence. And here we can see some depictions of the debate through art. For example, here you can see Newton and Huygens depicted as boxers, one of which sends through his eyes light waves, this one being Huygens, and Newton sending through his eyes particles. However, almost 100 years after both Newton and Huygens had proposed their theories, it was English physicist Thomas Young who would perform an experiment that strongly supported the wave-like nature of light. Because Young believed that light was composed of waves, he assumed that some type of interaction would occur when two light waves met. To test this hypothesis, he initially used a vertical surface containing a narrow slit to produce a continuous light beam containing waves that propagate in phase from ordinary sunlight. When the sun's rays entered the slit, they spread out or diffracted to produce a single wave. Secondarily, he allowed the light to illuminate a second screen with two closely spaced slits. In that case, two additional sources of coherent light, perfectly in step with each other, were produced. Light from each slit traveling simultaneously to a single point halfway between the slits and the second surface reached at the same time. The resulting waves reinforced each other to produce a much larger wave. However, if only one point is considered, one would say that the light from the distant slit would arrive after the light from the closer slit. So these two waves would be out of step with each other and might cancel each out, produce darkness, also known as gaps. Of course, today it should be noted that light presents both wave-like and particle-like properties. However, we're not going to analyze this in this presentation. And now we can say how you can create the double-slit experiment at your home. So, you're going to need for the construction a small sheet of thick paper, preferably a photographic paper, scissors, a tape, which is optional if you have other means of stability, a cardboard cutter, a laser, which can be found even in a presentation pointer like this one, a magnifying glass for precision, which is optional if you think you have great vision, and a stand for the laser and the paper, preferably made of wood or by aligning holding stands for stability and portability, which can be found in a physics lab or at home. But now, caution please. Do not use the laser by pointing it at someone's eyes, by not closing it when using it, by not placing it in a stable position where it can fall and accidentally be pointed at someone's eyes, or if you have a cat in the room. So now, we are going to set up the model. So you're going to need to make two parallel small incisions 1 millimeter apart from each other, or closer, if you're able to, using the cardboard cutter. You can also use the magnifying glass for precision and a ruler to make them parallel. Second, place the pointer in a stable place, like the stabilizer, as we said, the stand, in a way that the beam passes through the incision at a 90-degree angle. And please keep this in mind, because otherwise the results might be different. And third, you can use a piece of paper or a wall to display the result. And then observe. Here you can see the construction which I made for the experiment, which includes a laser, which is stably held by two pieces of metal, which I have put in a wooden plank. And also I have made a small construction to hold the paper in place, from which, as you can also see here, if you can see, there is a small slit, actually two slits, which will help us with the experiment. So now, let's observe. The light is spread out, but instead of a continuous line, it appears in parallel dots. Thus, this could mean that light is making a wave-like movements, indicating that it acts as a wave. So, as you can see here also, we have the result of the experiment that I personally did, and we can, through this way, reach the result that when light is passed through the incision, the beam spreads and becomes wider than expected. This important observation lends a significant amount of credibility to the wave theory of light. Like waves in water, light waves encountering the edge of an object appear to bend around the edges and into its geometric shadow, a region that is not directly illuminated by the light beam, since the middle part of the slit is covering it. The interference pattern also proves that the particle nature of light, even though that wasn't observed by Thomas Young himself in 1801, but rather was discovered as part of the photoelectric effect effect by Heinrich Hertz in 1887 and was also explained by Albert Einstein in 1905, for which he was awarded the Nobel Prize in Physics in 1921. And now you might be asking, what does that mean, that light acts as a wave? You might ask, can particles behave like that? Well, no, because if light consisted exclusively from classical particles, then the pattern size would depend on the size of the slit proportionately and would essentially appear as the shape of the slit in the wall below us, behind us. However, as you can see, the opposite happens and the beam is refracted towards the outside. Thus, it means that light cannot exist only as particles and that it needs to exist as waves too. Thus, you might be asking, why is this experiment so significant? Well, as we said, the double slit experiment provided important evidence for the wave-like nature of light and laid the foundation of quantum mechanics, which disproves the classical understanding of the world and dictates that particles can behave differently depending on how they are observed in a probabilistic nature. Thank you for your attention, and I hope you enjoyed the presentation.
Thank you very much, Omiros. Congratulations once more. Now let's